Okay, let's now get back to the viscous instability study of a parallel boundary layer. Here in a nutshell, we can follow the step. This is our governing equation for the disturbance quantities given in terms of the amplitude of the normal velocity. You also realize that normal velocity could also represent the amplitude of the stream function, because if I take a stream function like this, suppose I represent a disturbance stream function like this in terms of phi, y, say alpha omega naught, and e to the power I alpha x minus omega naught t d alpha. If we do this, then you can see that the v velocity that we are talking about there will be del psi del x with a negative sign, and that will give you minus I alpha phi e to the power I alpha x minus omega naught t d alpha. So, you can see whether you ascribe phi with the v velocity amplitude directly or the amplitude of the stream function, it is essentially the same thing. So, that is what we need to keep in mind, and what we did was that we noted this was a stiff differential equation. We converted them into this 6 set of first order coupled ordinary differential equation for the compound matrix variable y 1, y 2 to y 6. And these variables have the property that they satisfy the fast stream condition. So, that is what constitutes the initial condition. We have normalized them with respect to y 1 and we get the 6th condition, right. And so, what you do is you start solving this 6th equation with this initial condition and come up to the wall and investigate if y 1 is equal to 0 or not. That is what we call as the dispersion relation, and so that will have a real part and imaginary part. Then we talk about a grid search method. In that grid search method, what we do is we look at the 0 contours of y 1 real and y 1 imaginary. Wherever they intersect gives us eigenvalues. The collection of this eigenvalues are what are called as the eigenspectrum. Okay. So, once we have the eigenspectrum, we need to do something more, and what that something more is basically we need to polish this eigenvalues better, because this gives you a kind of a rough estimate. This is a rough estimate of those eigenvalues. You know how to do Newton-Raphson search. How do you do? Well, that is what let us spend a little time talking about Newton-Raphson search. First of all, we note that we are in search of eigenvalues which corresponds to the spatial instability problem. So, what you do is we fix Re, the Reynolds number, and omega naught, and obtain complex alpha as the eigenvalue, right. So, what we are going to do is basically we go through this exercise that we talked about. So, these two are fixed, Re and omega naught is fixed. We start off with some kind of initial guess of alpha, march down up to the wall, investigate what is the status. If it is not 0, then it is not an eigenvalue, and I told you that this is the way we find it out. So, that gives you a kind of a initial guess for the eigenvalues. Then what you do is you do what is done in a shooting method, right. We start off with that value of alpha. Again from the free stream we come and we check for y 1 at the wall. Now, in Newton-Raphson search, we will be a little more demanding. We will be looking for the desired precision. We will say, look, this 0 that we are talking about, it should be 0 say up to the 16th decimal place, accuracy and so on and so forth. Once we do that, we see that it's not satisfying, and then what you do is you basically want to find out y 1, which I will call as the new value in terms of. So, this is at the wall, right. So, this what we will say is y 1 at the wall, what we obtained as this, plus I could obtain d y 1 wall d alpha into alpha nu minus alpha old. So, what we are talking about, we have this imprecise old value. So, we want to put this value to be equal to 0. So, if I do that, this will be 0, this one will be this, plus this I will have a numerical estimate. Numerical estimate will give me some kind of estimate of this kind. So, this I would be evaluating where? Corresponding to the old condition, right. So, this is basically corresponding to the old condition times well alpha nu minus alpha old. Okay. So, what do we get from here? We do get this value, right. What this value is going to be? I will first take this on the side, divide by this, and then add to that. So, I will find alpha nu should be equal to alpha old minus y 1 old divided by this quantity delta y 1 w by delta alpha, right. So, this is your Newton-Raphson search actually. So, basically it depends on how accurately you evaluate this first derivatives and how these two quantities are with respect to each other. If they are close to each other, then the subsequent terms are negligible, right. That is the whole idea. So, that you can just simply take this first order representation and get an estimate for nu, and you can keep doing it again and again. That is the essence of Newton-Raphson search, and you find it out what you get. So, at the end of that activity, you are going to get an estimate for alpha real and alpha imaginary, and that is what we like to plot. What I have shown you here is a plot of alpha imaginary in RE omega naught plane. Now, this is something what we have talked about in the spatial problem. We fix the frequency omega equal to omega naught. However, when we write this, this actually requires an approximation. What is that approximation? That I am exciting the system at a frequency omega naught, the response of the system is also omega naught. How good or bad this is? You know, we are looking at linear dynamics, right. This is a linearized perturbation equation. So, for a linear system, one would intuitively say that this is a pretty good approximation, and this is what is called as the signal problem. And the essence of the signal problem is inherent in all published material on stability theory, except some of the work done by us. About a couple of decades ago, we started thinking fundamentally why this has to be so. You know, any good research starts with an innocent question, and you should ask that. If you want to do something fundamental in research, this is the way you should ask. Why did we ask that question? We are looking at linear system and we are exciting the system at a frequency omega naught. Why shouldn't the output be omega naught? Why there should be inconsistency? We got to understand it because we have already seen that this is not a ODE. The equation, Orson field equation is ODE. Why? Because we are looking in the wave number plane. So, that space dependence has been masked there. So, it is not simply an ordinary differential equation. If it was ordinary differential equation, then giving omega naught and expecting omega naught in the response field is perfectly justified, but we have a space time dependence of the problem. And in a space time dependence of the problem, we have what we called here as the dispersion relation. It may so happen that the initial transient at initial times, the dynamics may be more complex than what you are used to expecting from a steady state assumption of signal problem. That assumption relates to what will happen over a long time, but in the initial phases of the evolution of the variable, it is quite unlikely that you will only see omega naught. We will talk about it in greater detail. When we do not do such an assumption, what do we get? So, what happens is, in this case, we are assuming a signal problem and this is what is the consequence. Plotted omega naught in the y axis, Re on the x axis. Re is defined in terms of the boundary layer edge velocity, the displacement thickness and the kinematic viscosity that we are quite familiar with. Omega naught is a circular frequency that we can relate to the frequency in hertz by multiplying by 2 pi, and we non-dimensionalize it by multiplying it by a time scale, and the time scale is the length scale by the velocity scale. So, this is our omega naught 2 pi f times delta star by u e. What we have done here? We have reorganized it. Then what we have done here? We multiplied this 2 pi f with nu and divided by u e square. So, that we have a u e upstairs and delta star is as it is there, and we have multiplied by nu, we divided by nu. So, what happens is omega naught is now a product of two quantities f times Re. Omega naught by itself is non-dimensional, Re is non-dimensional, f is non-dimensional. So, what is this f? Capital F. Capital F is the non-dimensional frequency in which was stated in hertz, that we have converted into a non-dimensional quantity given by the expression within this bracket. So, if I tell you to study the property of a shear layer for a fixed frequency f, then what you should be looking at? You would be looking at a constant f, right, constant f value. And what is that constant f? F is here, f is omega naught by Re. So, this is like if I want to keep f equal to constant, that has to be a straight line. So, that is what we have done. We have drawn many such straight lines, and the straight lines each one indicate a particular value of this f, capital F or lowercase f. And what happens? As the f increases, the frequency increases in hertz, we go from here to here. And when we go this way, then we see that for each of these combinations we can find out the alpha or alpha I value. So, in this whole domain I have a map of what the value of alpha are and what the values of alpha I going to be. Once we look at that, we plot those contour lines of alpha I. What we have done here, the constant values, and we notice a feature of this particular 0 pressure gradient boundary layer, that there exists a line along which alpha is equal to 0, that is drawn by this solid line, and this line along which alpha equal to 0 corresponds to neutral stability. So, that is why this curve is called the neutral curve. So, what we have done here? We have drawn a neutral curve. What is inside the neutral curve? Neutral curve is the locus of alpha equal to 0. Inside alpha is negative. So, that means what? That region corresponds to instability. Okay? Whereas, outside the neutral curve you have a stable region. So, now you see what happens. Suppose I start off from a point A. So, at this point A, I try to track a frequency corresponding to f1. Then what happens? This frequency will traverse along the straight line all the way up to point B. It is in the stable region, right. So, whatever disturbance that I am looking at, it will decay up to B, then it will start amplifying. That is what our theory states, and this will amplify and reach C. That is again the extreme where it is unstable. So, beyond that again it will become stable. Now, you also notice the feature of this curve. Feature of the curve is that of course, the instability picks up the rate at which it grows. It becomes more and more as we come inside, and then again after some point the contour values start dropping off, right. So, it increases in amplitude in terms of intensity of the instability, and then again it decreases, becomes neutrally stable, and then it becomes stable. So, this is what we do. And now, suppose at the same location, instead of looking at this frequency f1, we are looking at a frequency f2. f2 is greater than f1, right. And then what we notice that from point P to Q, again you have a disturbance decaying, then Q to R it will amplify, and then again it will start decaying. The shape of this curve is such that we have a line which we could draw it like this, which will be tangential to the tip of this neutral curve. What happens to those frequencies on this side? They will never be unstable, they will be always stable. So, this limiting position where a straight line drawn from the origin simply touches this neutral curve defines a Reynolds number, below which flow is stable for all frequencies. Okay. That particular Reynolds number is the critical Reynolds number, because it says that below that critical Reynolds number everything is stable according to this parallel flow theory, linear theory of spatial instability. So, got to remember that this is roughly around 519 for the Blasius profile, and this is what we should keep in mind. And how good or bad these results are, we will come to it later, but let us now look at some of this other features. We have talked about this. Now, you saw that neutral curve was something like this. Okay. Let me show you something also, which is perhaps in the next slide. This is what we need to look at. Well, we are now looking at the alpha r contours, the real part of alpha contours. Again in the same RE omega naught plane, and again what we are doing, we are drawing the constant alpha r contours, which are like this. What is this solid line? This is that neutral curve. We have just simply kept it for our reference purpose. What we notice that if I follow a constant frequency disturbance, then what it does, it migrates from one alpha r constant value to the next. If this variation is gentle, then what are we going to see in terms of the disturbance profile? That it is slowly going to adjust itself to the local condition. This is one of the driving motivation for using the stability theory, that we expect the flow to locally adjust itself to the prevalent condition. Okay? and that is really bolstered by looking at these gentle curves. They are going rather very gentle manner, and this was one of the interesting point that people did observe experimentally later, that indeed the disturbances do latch on to the local property, and that is what people have looked at. Now, let us also look at one particular aspect is the tip of this curve. If I look at the tip of this curve, the corresponding alpha r value is roughly around 0.35 to 0.36. What does that mean? Alpha r is the wave number, that is 2 pi by lambda, and this alpha r is increasing. So, there is a critical minimum wave number below which everything is going to be stable, right. So, that is what we have in the transparency written here, that we have a case of alpha maximum, that is roughly, I just simply said it is about value of 0.35. Please do understand that all the quantities that we are displaying and we are noticing are non-dimensional. So, if what is the dimension of alpha? Alpha is a dimension of 1 over length. So, essentially what I am writing as non-dimensional alpha in a dimensional form, it should be like this, I multiply by the length scale. So, alpha max is 0.35 by delta star, and that will correspond to what? Lambda min, minimum lambda wavelength, that will be 2 pi by lambda max, and that is roughly about 18 delta star. It gives you some idea that in a Blasius 0 pressure gradient boundary layer, if instability sets in, you are going to see disturbance waves which are of the order of 15 to 20 delta star. You can't have smaller than this. All the disturbance wavelength will have to be about this and above. Okay. So, this is something we should remember. Okay. We alluded to that the stability theory works fine. I wish the story was that simple. You already know the story, right? The theory came quite some time early on, but one of the problem of the theory was that it was virtually not detectable, and the persons who really detected is a group from USA, and this is that famous paper by Schubauer and Kramstad, which was published after the Second World War. These work were done in and around the onset of Second World War, but this was published after the Great War. Now, what is it that you are seeing here? What you are seeing here is essentially you take a signal, okay? You put in a probe. What kind of a probe you do? You just put in a hot wire probe. You put in a hot wire probe inside the boundary layer and put the signal on an oscillogram, and in the oscillogram this is what you are going to see. So, these are fixed location. So, this is about 7 feet from the leading edge of the plate, this is 8, 8.5 and so on and so forth. And at each of this location, if you construct the corresponding Rex, Reynolds number based on current length, I think it is 10 to the power minus 6 scale, and as you see it, this is the way the signals look like. So, what our theory said? Well, our theories talked about some frequency amplifying over some distance and decaying outside that range. But what do we have in an actual scenario, that is where we do not impose any explicitly any scale, that scenario will be called a natural transition. So, we are not doing anything, we are just simply looking at a flow as it prevails, and this is how it looks like. So, in a qualitative manner, as you can see, there are wavy disturbances, but they are quite irregular. That is what we talked about this signal problem. But here we do not know how many omega naughts are there, because it is natural, right. It is not necessarily that you are going to get a monochromatic signal. That is one of the things we should understand, that your response field is going to be polychromatic. However, despite that, what you notice is this following succession, that some places you do get a fairly decent signal, which looks like a simple harmonic motion, right here, somewhere here. However, you notice that this signal, what you are seeing here, the trace has been multiplied, magnified by a factor of 4 to see this. So, otherwise if I remove this factor of 4, this will hardly be seen. This signal is magnified 3 times, this is magnified 3 times, 3 times, then we did not magnify it 3 times, we magnified 2 times, and this is what we get. And then these are not magnified at all. Now, as we can see that starting off from the leading edge, as we go along down the flow, we see that 2 things happen. The signal strengthens, amplification is seen. And what about the content, frequency content of the signal? Frequency content is quite dissimilar. See, that is what I have talked about this signal problem. What may happen, that initially I may have a band of frequency, but that band itself keeps changing as we go down. And this is something what you would like to call as post transitional flow or a turbulent flow. So, this is characterized by very high frequency oscillations. This is something we need to understand, that 2 things happen in actual flow. The linear theory, even though it is all right, it is going to be valid when the amplitude is smaller, because amplitude grows, then we see a qualitative change in the flow pattern. This actually suggested something to those group of scientists in National Bureau of Standards. They realized that if you want to really probe, that instability and transition in a flow, you cannot depend upon natural transition. It's very, very irreproducible, because I could take the same plate and I could go in another tunnel, maybe in the same lab itself, but in another tunnel, and I will do the same thing. I will see the oscillogram trace and I would see something different. Why? Because the disturbance background is different in different tunnels, right. So, what one needs to do actually then, one needs to do what we call as the receptivity studies. The receptivity studies imply the following, that you try to take out the background disturbance as far as possible, move it out, and then you want to test the power of the theory. So, you create a single monochromatic signal and then trace it, what happens to it, right. Then you are going to validate whether you have a good theory with you or not. So, for example, we want to, let us say now, follow a fixed frequency f1, and we have already talked about this neutral curve, have this thumb shape size, and the lower branch is called the branch 1, the upper branch is called the branch 2. This is the usual terminology. So, what happens is, if I now plot minus alpha I versus x, so this is minus alpha I versus x, then what happens between this 2 points, I would have growth, unstable region, right. So, this is the unstable band, and outside these I will have alpha as positive. Okay. Now, what have we already seen from the spatial theory description, that I can calculate this spatial growth rate as minus alpha I, which is nothing but 1 upon a dA dx. So, this is rather easy, isn't it? dA by a equal to minus alpha I dx. So, I could integrate. So, ln a equal to integral of alpha I dx. Then of course, I can take that. So, what I have done is, I have written it down that ln a, I have gone from an initial station x naught to some current station x. At that initial station x naught, let me call that amplitude a naught. Then at the current station, I have the amplitude a of x. So, a of x is nothing but a naught e to the power minus of x naught to x a alpha I x dx. Why did I put this x within parenthesis of alpha I? Again the same thing that we talked about, that this is what we are expecting. We are expecting that the flow will latch on to the local condition, right. That is why we are saying that my theory is based on locally parallel flow approximation, and I have collected those values, I have gotten those diagrams, but then what I am hoping for the flow to do is latch on to this local condition, and then what I am getting is that alpha I is a function of R e, because different station has different R e, and then I integrate over it. So, this is an exponent, right, minus alpha I dx, which I call as n. And now, this n that we have obtained is for that frequency. So, this n itself is a function of that particular frequency. So, different frequency will suffer different types of amplification, right. So, this is one of the way that we like to do. So, what we find that we are integrating alpha I dx, and alpha I minus alpha I goes like this. So, if I integrate it, it will go like this. It will continue to grow, but the rate is going to change depending on the location, but beyond this of course, it will decay. So, if I start my datum at this point in the unstable band, this n value is going to increase, it will reach a plateau and again start falling beyond that unstable band. Now, this basically tells us what to expect. Well, this is what we expect. Things are getting interesting, right. What happens? Again we are plotting now R e on this axis, R e or the streamwise distance, and on this axis what have I plotted? I have plotted ln of a by a naught. So, that is essentially that integral minus alpha I dx or n. So, this is that n value, lowercase n value. Then for different frequency, I do get this different curves. Do you all agree with the general feature of this? Yes, because you can see that if I draw the neutral curve, this is the way the neutral curve is, right. Now, if I look at a low frequency, then what happens? It enters the unstable region later and exits also later. as compared to let us say another higher frequency which will be like this. So, that will enter here and exit here, whereas this is entering here, exiting there, and that is precisely what you are seeing here. The lower frequencies that we are plotting here, they start off late, they grow and they exit also late to a larger band, whereas a slightly higher frequency you would see starting off earlier, exiting also earlier. And what we notice also, because the range, basically we are taking a horizontal projection of this. So, the extent is going to come down, and that is what you are also seeing, that as your frequency is increasing, your extent of unstable band is decreasing. So, for this is about from 1000 to here, for this it is about let us say 1300, 1400, all the way up to about 2400, 500 of that kind. So, this is the story that we are going to envisage, and what we find that all this begins at that Re critical we talked about close to 519 or something, or here we have written 520. Now, what happens is different frequencies are given by this sort of curve. So, I could draw an envelope shown by this dotted line, and this dotted line is basically a locus of all this different maximum that we have for different frequency. That quantity is what we call as capital N. So, this is somewhat like this, that as I go along, some disturbances are going to grow, and different frequencies will have different growth rate as given by this. So, we talk about a fixed frequency growth for a fixed frequency, and we can talk about a total amplification, as if that as we are going from one station to another, this amplitude is going to translate into the next frequency, and so on and so forth. Then your disturbance has grown along the dotted line. See, these are all very approximate engineering ideas, and what we are talking about, this is our ln of a by a naught. So, if we have ln of a by a naught as given by that dotted curve, which we have called as capital N. So, essentially what we are talking about then okay. So, that means what? So, basically n kind of signifies the exponent which the maxima will tell us. Okay. Now, let us say a few things. What people do then? What is unknown in stability theory? We do not know what this A naught is. We cannot say, right? We are talking about relative amplification. That is what we are talking about, and that determines on this n curve. So, for different frequency we have different lowercase n, and the global envelope tells you about the capital N. Okay, so, now basically then that is the story of disturbance growing inside. What was achieved by this specific experiment of Schubar and Skramstad was basically identification of that Re critical, and then tracking a fixed frequency disturbance, the extent of growth range, and so on and so forth. Those are the success stories of the stability theory. Even today, this theory is very extensively used in analysis and design of the aircraft wing. What you do is basically you try to obtain this n curves. Here the n curve that we have obtained is for a 0 pressure gradient boundary layer, right. So, if I am trying to design a wing, think of what we need to do at each and every stage. See, these are all kinds of local adjustment of the flow, and let me also tell you a little bit in advance that a pure hydrodynamic scenario like the way we are discussing in this course, things do work out. We just simply found out very recently that if you add heat transfer, this linear theories stop working. So, please do not get too carried away, because you would be coming across various claims where people would say, oh, we use a very sophisticated theory called e to the power n method, and this is your e to the power n method. This is not theory. This is of course theory to the sense that you have idealized the actual flow in terms of a locally parallel flow, and you have obtained all of that. And now, in actual geometry, what will happen? You are going to get all kinds of pressure gradients. So, think of the aircraft wing design. I would have at different station different pressure gradient, right. It is not going to be a flat plate. Of course, you calibrate and gain confidence from a standard geometry and standard result, that is the Blasius profile. You are happy that you have done it, but now if you want to go and use it for actual practical scenario, then what you are going to get? You are going to get a variable pressure gradient flow, and what we are then talking about, we are talking about different mean flow profile. As we go along over the wing at different stations, we are going to have different mean flow profile, and here are some profiles plotted for your benefit. Now, this one here indicated by the 0 and 2.59, this actually is your 0 pressure gradient boundary layer. How this thing is defined? It is defined by how the edge velocity varies with x. That edge velocity variation is given here by a similarity parameter, which is called as Faulkner-Scan parameter m. What is this m? M, as we have written, you will see it is nothing but 1 over u e d u e dx. So, what we are talking about is, say we are talking about flow past a aerofoil like this. Okay. Now, what is happening? Now, as we go along, we are going to get a different kind of boundary layer. So, I can get u e as a function of x just outside the shear layer. From that u e versus x, I can convert the values of m. So, please do understand that m itself is going to vary along. Okay. Now, there is another quantity that is of great significance in boundary layer theory, is called the shape factor. Shape factor is called h, and which is nothing but delta star by theta. Well, this we have already identified as displacement thickness. This is what we call as the momentum thickness. Okay. Well, the very nomenclature will suggest what these two quantities are. Both are some length scale, right? We are talking about thickness. One talks about displacement. What does displacement mean? It is as if a streamline has been displaced by that amount due to the viscous action. Because what happens? Ideally, we would see outside the shear layer will have the inviscid streamline, but as we come closer to the surface, it has to adjust itself so that you satisfy the no slip condition. So, this is equivalent to as if the whole flow has been lifted up, displaced. That is what is given there. So, for an incompressible flow, what is the definition of delta star? 1 minus u by ue dy, and this we can do it. So, this is what it is. Ideally, it should have been equal to 1, but the viscous effect has brought it down to u by ue. So, we integrate over the whole width to get delta star, and theta is defined like this. You are going to tell me what does this. Those of you who have done a course on boundary layer theory, I hope all of you have done. If you have not, then I may like to spend a day or two later, but at this point in time, let us talk about what this is. Do we have any idea, anyone? Are you familiar with the momentum thickness? Have you done it before? You have forgotten? You have? So, this basically tells you about the momentum deficit. See, ideally, what was the momentum carried through with the fluid? If you did not have any viscous action, it should have been u is half rho u square. But then now what you have locally? You do not have u e, but you have u. So, what happens is that what is being carried through with the mass is given by u, rho u. Ideally, it should have been rho u e. So, this first factor gives you about what is the actual real mass flow. Now, the second factor tells you that loss in this momentum because of viscous action. Ideally, it should have been 1, but it has come out to this. So, this is the kind of a loss. So, this is the actual mass flow times loss. So, that will tell you about the momentum deficit. So, basically theta tells us about the drag, and this drag, this component of drag comes about because of the no slip condition. So, this drag would be related to the skin friction drag. Okay. So, this is what it is. So, theta gives you an estimate of what kind of momentum that we have lost due to the shear action. Okay. And the shape factor tells you about the quotient of this two length scale, delta star by theta. And what we have done here is now the mystery of those two parameters will come. The first 0 that we identified as the Blasius profile, the top 0 represents m, m is equal to 0. If I have a 0 pressure gradient flow, then what happens? d u e dx is 0. It does not change, right? 0 pressure gradient. We can see that, can't we, from Bernoulli's equation if we are looking at the outside flow. So, m is equal to 0 corresponds to Blasius profile, and corresponding h happens to be this number 2.59. Okay. So, that is this line, the second line, second last line from the bottom. Now, what I could do is I could create a flow of different value of m. What is m negatives signify? M negative signify d u e dx, negative means u e is right. So, what would that mean? Okay, so that is an adverse pressure gradient flow. So, This case then corresponds to a value of m equal to minus 0.1 and corresponding h has turned out to be equal to 2.8. So, should h increase or decrease for adverse pressure gradient? You look at the velocity profile that has been drawn here. If u was equal to ue, then I would have had the profile straight away here 1 and then it would have gone. So, compared to 0, this curve is displaced upwards. So, it has more mass defect, right, and then what happens? Corresponding momentum defect lags. So, what happens is the numerator increases, denominator does not keep pace with that. So, overall h actually increases. So, that is what you are seeing, that m has become negative. So, you have adverse pressure gradient and h has increased. Okay. The other scenario of course, would be the case where m will be positive and then the corresponding value of h will be lower. Let us first talk about the adverse pressure gradient little more. You can see that because of the adverse pressure gradient, the velocity profile becomes deficient closer to the wall, and you come to a stage where this curve actually has a slope of equal to du dy equal to 0. That corresponds to your separation condition. The skin friction locally becomes 0. Right? That is what is the value given here on the for the top curve. Corresponding m is about minus 0.19888 and h becomes 4.03. So, what happens is, if we keep on having this adverse pressure gradient, the boundary layer becomes thicker and the flow has a tendency to separate, and that is the limiting value. Whereas, this is the other case. This case m equal to 1 we will talk about in the next class. We will discuss it in somewhat greater detail when we make the next time. Okay.